All right. Hi, everyone. Thank you so much for coming to the very first CASE seminar of the semester. For those who are not familiar with CASE stands for Center for AI and Society here at USC. There's a lot of researcher, practitioners participating in this center. We're very passionate about AI for social good. And so a lot of the talks, including this one that you're here today, are going to be evolving around that topic area. I'm super excited to have Dr. Angela Zhou to join us today to kick us off the very first talk of CASE this semester. I'll just do a brief intro for Angela. So Dr. Angela Zhou is an assistant professor at USC Marshall. She's in the data sciences and operations sectors of Marshall, also with courtesy appointment at the Department of Computer Science. Previously, she did her postdoc at UC Berkeley and received her PhD from Cornell University. Her research examines data-driven decision-making under uncertainty that includes operations, statistical machine learning, causal inference, among many others. And her amazing works has been published at various top-tier venues, including UNLIBS, ICML, AI Stats, and FACT, and among a lot of other great places. With that, please join me in welcoming Dr. Angela Zhou for today's talk. Thank you.
All right, thank you so much. Before we get started, let me know if I'm not speaking loud enough. Also, there's still some open chairs in the front here. It's a very funnily designed room. It's very narrow and very deep, and the font on my slides is pretty small. So, so feel free to move on ahead. So it's great to be here giving a seminar for CASE. In the spirit of CASE, this work has some applied angles and some methodological angles. So I'll be trying to discuss both in some detail. But I'm also happy to take questions if you want to kind of like deep dive one way or the other. So I'll be talking today about batch adaptive causal annotations. This is some general methodology that we developed, motivated by a kind of like long-going collaboration with a nonprofit in homelessness services. So I'll also start by introducing that collaboration and some of the motivation as well. This is joint work with a great PhD student, Ezne Nwankwo. She's actually at Berkeley EUCS. Kind of long story how this team got put together, but she's also on the postdoc market right now. Also, our amazing collaborator, Lauren Goldkind. She's at Fordham University Graduate School of Social Work. And a lot of people at the nonprofit Breaking Ground have been talking to us very kind of like helpfully, helping us to understand the data and help us scope use cases. So this first initial work you can think about as like a methodological part 0, and I'll be describing some of our kind of like ongoing and future directions as well. So I'll start with a rather maybe like longer than usual introduction, because I think this kind of Casenotes data that we're working with is a little bit different than the typical data that we work with in ML, or let's say like other kind of benchmark data sets. I want to talk about like what is the value that AI can potentially add to this nonprofit as they are trying to leverage information from this text data. So I'll describe our motivating collaboration. What does the nonprofit do? Where does the Casenote data come from? And then I'll kind of narrow in on the motivation for our kind of narrow methodological contribution. So first of all, our kind of like high-level collaboration goal was to kind of understand this nonprofit. They conduct street outreach for homelessness services, and that's a very intensive outreach program. It kind of started off with, in the very beginning, this was a pilot program where they would reach out to all of the unhoused individuals in Times Square and try to move them into housing. And so that's a very intensive, individual-oriented approach that has been scaled up to now be a citywide program. And so, first of all, I should say that most of our primary expertise is in causal inference and causal inference and machine learning. So our kind of ultimate goal, or one ultimate goal in this situation might be, we want to understand what is the impact of street outreach, kind of more or less outreach services, on the progress that a client makes towards, let's say, completing a housing application, starting or completing a housing application, or towards a housing placement. And so this is just an excerpt from their impact report. So why is causal inference useful to these nonprofits? It's useful to report out the impacts of their activities on relevant outcomes. So the nonprofit kind of advertises top-line metrics to various funders and other kind of like more executive parties about, how many people have they served and how many housing placements has that resulted in. On the other hand, when we take a look at these kinds of top-line metrics, the thing is that the nonprofit doesn't have complete control over housing placements. They do a lot of work in outreach, but ultimately what they can do is help someone complete housing application. And actually, it's other organizations, the city, that manages the actual placement process. So this kind of top-line metric is a little far down the line. If I were just looking at this, as a data science person, I'd say it's a little high variance. If I were looking at this from like an RL lens, there's all kinds of like credit assignment questions associated with such a down the line metric. So this is part of our motivation for trying to extract these intermediate outcomes or outputs from this case note data. But that leads us to a kind of like even more fundamental question, which is, in a basic sense, how can we reliably work with case notes at all when there's just too many case notes for any single person to read? And obviously, in the age of LLMs, we can probably incorporate LLMs to help us make sense from these case notes. But we also want to do that in a way that preserves kind of valid statistical inference. So that's some of the broad level motivation. What is it that the nonprofit does? What does street outreach look like? So the street outreach program, what they do is they reach out to unhoused clients on the street. They kind of inform them of the services that the nonprofit provides. If they see someone multiple times, that provides evidence that someone is kind of chronically homeless. That kind of opens up eligibility categories for them. The outreach teams work with the clients to inform them of various services that are available, help them apply for benefits, help them understand the kind of complicated housing landscape, inform them about different kinds of placement outcomes, and ultimately, they are their kind of like primary instrumental goal is to complete a housing application. Although, if you talk to outreach workers, they'll describe the work as much broader, just social work in generally, in terms of discussing with clients and so on. But a primary instrumental goal is to complete an application for housing. So this diagram illustrates there's many different steps along the way. This is a kind of repeating mantra of kind of understanding the outreach landscape. This is another diagram that I found very helpful just to understand what outreach looks like. It's a really kind of like longitudinal relationship without kind of like fixed time steps. So there's a lot that can happen. A lot of it is very unstructured. So what is this? This is a diagram from an older kind of like service journey map that New York City Service Design Studio produced, where they tried to put together a picture of what are all the entities that someone unhoused is going to talk to, kind of like along their way to completing an application. And the main takeaway here is that it's a very long and involved process. This report is 70 pages long. They talk to a lot of different kinds of service providers, different kinds of offices to collect all different kinds of paperwork, documents, replacement documents, complete various appointments, and different kinds of administrative checkpoints along the way to housing. So just to give a picture of what this data looks like, each of these interactions, the pairing of like a yellow client, a yellow dot and a purple dot means a client is meeting with an outreach provider. And each interaction, after each interaction, the outreach provider writes a short case note, kind of just describing what happened. And these case notes kind of like comprise the data set that we're looking at. So the main point, there's a lot of unstructured interactions that happen alongside a kind of like maybe more structured bureaucratic landscape of, what do you need for the application? You need these things, you need these documents. So some themes that show up in the case notes. Once someone is on caseload, they're seen quite regularly. So the good thing is that we have, there's a goal to have good coverage for people in the data set in terms of this case note data. Some themes that occur, if we think about a kind of prototypical, or if we try to think about a linear way this might look like, most client trajectories do not look linear in this way, but they would start by kind of building rapport, learning about the clients, learning about their goals, kind of like the relationship, and then really the client has to express interest in applying for housing, and that kind of really kickstarts this kind of completing this bureaucratic process of, to complete the application, you need to get these documents, you need to get replacement documents, you need to go to these appointments in all these different offices, so on and so forth. And then it comes to the part about eligibility screening and kind of like waiting for a customer. So this is kind of like what happens. This, from our reading of like different ethnographies and other places, this is maybe not super atypical for outreach in general. So there's many of these case notes. There's different themes, there's different milestones that can be measured in the case notes. And maybe the most important thing to point out is that none of these milestones are really recorded in the tabular data or the databases of the nonprofit. There's just many different ways that these milestones can occur. They're interested in, for example, revisiting their data collection, but you also don't want to have kind of like social services outreach workers choosing one box out of like 200 boxes of a checklist of what could happen after every service interaction. So there's some way in which this is these are very unstructured interactions. There are some top line things that you can maybe tag or categorize. But there's a lot of, but you don't necessarily want to try to enumerate everything and turn that into a checklist that the outreach workers should provide. So in some sense, a lot of these milestones may not ever make it into structured data fields because what they're doing is just super unstructured and very open world. So one of our work streams is trying to do a version of qualitative coding, let's say, where we're trying to code these different kinds of intermediate milestones that appear in the case notes. Now, of course, the case notes, they're fairly short, often limited. A lot of discussions about who writes good or not so good case notes. So we're focusing on coding things that are, let's say, like more objectively measurable, or things that don't really get discussed in many different ways. So that's the nice thing about this bureaucratic thing that they're trying to do. There's a kind of fixed set of entities or objects. You need a birth certificate, you need, some 1 out of like 10 or 15 kinds of documents. And so we're really focused on trying to extract that kind of structured milestone from the case notes. Of course, this misses a lot of the very relevant and important part of social work of really building a kind of interpersonal relationship. But by and large, that also does not necessarily appear in the case notes either. So this qualitative coding, we're missing out on a lot of what happens, but is at least maybe a favorable match for the instrumental goal of completing housing applications. So that's one work stream that we're interested in. And if we're able to do this kind of qualitative coding at scale, then we can start to ask questions like, what is the causal impact of more or less street outreach on helping clients make appointments, or completing appointments, or starting a housing application? All these kind of intermediate milestones that are prior to the more down the line housing placement. So to kind of jump to our methodological proposal, we're going to start with this kind of like causal task in mind. We're going to say we want to estimate the effect of more or less like street outreach, let's say, on some kind of outcome of interest. that we would like to extract from the case notes or code from the case notes in this way. So what we're going to do, so we're starting from the case notes, and essentially we're trying to figure out the best way to combine ground truth data annotation with cheaper but noisier LLM prediction at scale. So LLM data annotation has really exploded in the past few years. It can give you like, some percentage of the way there, but it's always going to have errors. On the other hand, ground truth human annotation is really, gold standard, best in class. If you kind of ask an outreach worker what the case note is about, they truly have the best idea of kind of like, what is happening. There's so much like organizational knowledge in these case notes that it really is the gold standard. But it's just really cumbersome to read all these case notes. And our understanding is that no one really reads all of the case notes. What we'll have to do is figure out what is the best way to allocate a limited amount of ground truth annotation. So let's say we have a budget for data annotation, some percentage of the data set. We'd like to combine labels from these experts and from, let's say, noisy data annotation from LLMs or other kinds of AI machine learning predictions. And we like to figure out how to annotate this data in a way that results in the best kind of statistical estimation for our downstream causal question. So this is what the kind of like our first methodological project is about. How do we optimally sample these instances for the outcome annotation? So ultimately, we'd like to continue with this and work with the codebook as well, but that's kind of ongoing work to code the data sets as well, or the relevant portion that we're working with. And the last thing I want to mention is that I really focused on talking a bit more about this nonprofit, what street outreach looks like, what case note data looks like, and why case note data is so valuable. But we believe that this situation also mirrors a lot of other situations. So case notes appear a lot in social services in general. One kind of like large parallel is clinical notes and natural language processing. Another thing that happens often, there's a lot of like navigation or like patient advocacy where people are helping people navigate what is underlying like a it's a complex bureaucratic system. And we think that there's a lot of other situations where this can be helpful. So the introduction was a bit long, but I think that this kind of data is very different from the typical data that we work with. I think it also raises interesting questions about language, like how do nonprofits want to use language? Which ways do they use language when? Are really interesting. But I'll wrap up the introduction by how we kind of transition to our methodological contributions, which is now we're trying to think about data annotation as a limited resource, but we want to optimally annotate for causal inference. And so after this, I'll shift to more of like an abstract causal inference talk before we revisit the breaking ground data when we see kind of like the benefits of the method. So for the next part, I'll talk about the kind of general model we're working with, how we are thinking about combining these two sources of information. If you're familiar with kind of like causal inference or measurement error, the way that we think about this is that we're going to try to do optimal sampling of a validation set for causal inference, but without making any kind of measurement error assumptions. And what this means at a high level is that we're really treating the LLM as a black box. So we're not going to use any qualities of the LLM per se. We're just going to use the fact that we're picking which data points we're annotating to begin with. So what is the model for causal inference we're going to use here? So for our causal inference task, let's say the impact of more or less treatment on outcomes. We'll start with a kind of like typical setup where I'll use X to denote like covariates. These are covariates measured pre-treatment. They can help us reduce variance by predicting what's going to happen to this type of individual. We have treatment, Z. Z, we will start with thinking about the binary case. In the paper, we extend to continuous, and you can kind of repeat this logic for more complex situations. And we're going to call Y kind of like undecorated. We're going to think about Y as like the ground truth outcomes, which are actually not observed to you to begin with. In the causal framework, we're going to use Y of Z to denote the potential outcomes. So this potential outcomes kind of like notation or idea is the idea that every person, for every different value of treatment that you could offer, has some kind of like different random variable of how the outcomes would change under different levels of treatment. And the causal problem is that treatment was allocated one way in the historical data, and you didn't observe what happened under the other value of treatment. So the problem is that we don't actually observe the ground truth unobserved outcomes. So we can think about this as a kind of ideal data generating process. Instead, what we do observe are what I'm going to call kind of like Y tilde. So Y tilde, you can think of this as this like noisy text that you could go on and reveal the ground truth of at a cost. And we're going to think about Y tilde as really like a measurement of the ground truth of Y. And so I just want to pause for a second and emphasize this idea that we're thinking about trying to reveal a ground truth outcome Y that affects the kind of like noisy or high dimensional observation. This really follows a kind of like measurement notion of what we're trying to learn in terms of the ground truth. So if we think about different examples in different settings, you might think about this as like if we're trying to do something with ground truth annotating radiology images in AI or something like that. This is like saying that we care ultimately about some underlying like latent object, Y, that generates the image or the text that we see. And we're not actually specifically interested in like a style or like a characteristic specifically of the text. So we're not interested specifically in qualities of the text per se, except in as much as they measure the ground truth. So this is a subtle thing that will interact with some assumptions that I'll hide for the purposes of the talk. But which direction this error points can have some different implications for like NLP in general. So it's like a causal versus anti-causal distinction. So in terms of what is the data that we do observe, we're going to be thinking about sequentially revealing these ground truth annotations over time. So we're going to think about ourselves as working with a data set where we have an additional indicator R. R is 0, 1. R represents whether or not a data point is kind of like annotated with the actual ground truth outcome. So it's a missingness indicator. And therefore, our final data set suffers two sources of missingness. In one sense, treatment censors which version of the outcome you see, the outcome under treatment or control, as well as R controls whether or not you actually see the ground truth. So really, in our model, we're just working with these kind of two compounded sources of missingness. The treatment and the missingness of whether or not we can reveal this outcome or not. You can think about R equals 1 as it's annotated, it's revealed. Our ultimate goal is to measure an average treatment effect in terms of the ground truth outcomes, Y. So these ground truth outcomes, Y, are going to be fairly simple. For example, it could be like, does someone complete an appointment in 6 months or not? And the main point here is that we don't really care about treatment effects in the original high dimensional space of Y tilde, like text or images. So this is kind of like saying the change in case note descriptions it's kind of like too high dimensional and like not necessarily what we care about. We're interested in the change in these intermediate milestones that we are trying to extract from the case notes. If you think about what this means for like the medical example, this is like saying, I'm not interested in how treatment affects like the pixelness of the image, or like the 1,000 by 1,000 pixels. I'm interested in how it affects the tumor size. So that's just all that is like, that's all that is like different about that setup. The main thing that we're working with is that we are saying that given this data set that we have control over which data points that we can go ahead and sample or annotate to reveal the ground truth. So we're going to denote this by pi of z and x. Pi is ultimately going to be the decision variable. With what probability should you reveal the ground truth for this individual? And we're also going to assume that we're working under a sampling budget. So your total probability of sampling is going to be in some like percentage of the original size of the data set. And so obviously, if you had no budget, the best thing to do would just be to label everything, get the ground truth for everything, ground truth annotation for everything. So this project really makes sense when you really truly have a limited budget for data annotation. And we'll see how our results indicate that you'll get better improvement under low budgets. Now, the last kind of objects to discuss are related to those that are like more standard in causal inference per se. So we're assuming that we have this large observational data set that already records what happened with the treatment and the outcomes. So our typical things to estimate in that setting are what's called the propensity score, the probability of receiving some treatment in the original data set. So if this was a randomized controlled trial, if you gave treatment with half-half probability, then this would just be something simple like half. In this case, this just reflects typical outreach practices. And so this would be estimated. The other thing that is relevant to estimate is the outcome model. So from your limited ground truth data, you could try to predict what are the outcomes, what are the ground truth outcomes, just given the covariates. There's different ways that you can start to try to incorporate the high dimensional information as well. I won't go into details on this variance, but the problem is at a high level is if you just try to do this on a ground truth, you're not going to have enough data. On the other hand, using this outcome model can help you reduce the variance of your estimation, which is particularly helpful because in these kinds of domains, everything is high variance and outcomes are quite easy. Okay, so I've introduced the notation for the model, and now I'll discuss some kind of like baseline estimation strategies that we might consider, as well as what we're trying to do with the best in trying to achieve the best of both worlds. So, in a couple of words, what we could try to do is just try to impute the whole data sets with LLMs or something like that. We could also try to do standard proper causal inference on just the annotated data alone. So I'm not sure if the gray shows up on the screen anymore, but I'll use like this gold stripe to denote the gold data, how much ground truth data we have. So we could either run LLMs on the whole thing, or we could stick to our budget and like randomly choose where we allocate our budget and try to do like the gold standard in causal inference. We call it like doubly robust IPW or augmented inverse propensity weighting. It will use the outcome model to reduce your variance of the outcomes. And we'll use the propensity model to reduce the selection bias of selection into treatment. What we're going to do, the gray isn't showing up, so it's hard to see that, but we're going to try to leverage the LLM imputation on the whole data set and achieve the best of both worlds. So again, what are the problems with these two alternative strategies? If we run LLM imputation on the whole data set, we will generally have some kind of unknown bias, and we'll have invalid inference. And so the problem is really just we need some ground truth to ground the LLM predictions. And that's the main takeaway of this whole talk, is I hope to convince you that a little ground truth will go a long way in terms of grounding LLM-driven kind of like analyses towards something that can give you unbiased and valid statistical inference. And you can still leverage the kind of like scalability benefits as well. So the good thing is that that data set is much larger, unrestricted by the budget, and so the variance might be lower, but you'll be subject to some kind of unknown bias. On the other hand, if you try to just use the budget alone, the problem is you might have a very high variance estimate. So what we're going to do, now that we've modeled this problem as causal inference with missing outcomes, missingness has been very well studied in general. And so there is an existing estimator for causal inference with missing outcomes. It looks quite like the kind of like normal AIPW, or the normal kind of like doubly robust best estimator. The only difference is you add this extra layer of missingness. So you only use the ground truth outcomes where you can observe them. You impute everywhere else, and you have to adjust doubly for the selection bias into treatment and the selection of which data points that you adjusted for. But the point here is that now these are just two different sources of missingness. They kind of multiply each other, but in this situation, we have control over which data points get annotated. So that buys us a layer of randomization that allows us to use a lot of these tools for improving estimation. So this estimator is known to have really good properties. It satisfies something called like great double robustness, which means that we've introduced these new kind of things to estimate, like the propensity score, the outcome model, as well as the probability of missing outcomes. And you can still ensure valid estimation of the average treatment effect at much slower rate requirements for each of these different kind of like intermediate outcome models or propensity models that are not really the last thing that you wanted to estimate. So I'll mention related work just briefly. So this work kind of builds on ideas in a emerging line of work about that we might call like LLM-assisted statistical inference. So if you've heard about something like prediction-powered inference, for example, they're applying ideas like this, like how do we combine these two sources of data, given that we can leverage the fact that we can choose which data points to sample, and therefore we can truly randomize which data points to sample. They're using that trick for like standard mean estimation. So if you're like trying to estimate an average, they also extend this to other things that look more complicated. But the main point is that they're focusing primarily on like non-causal estimators. So our point of departure is really just that we're focusing on what happens if your downstream task is causal estimation rather than just non-causal inference. And the other thing is that we're optimizing the data annotation, or optimizing the sampling probabilities, which buys you a lot more in terms of budget savings. There's also a lot of work on kind of like surrogates and proxies using this kind of missingness to buy you more in statistical estimation. I'll kind of like skip this discussion. There's more in the paper. There's also a lot of cool work in homelessness services and AI. A lot of people at USC do a lot of really exciting work. And I just want to mention that one thing that we learned from this project is there's in AI and homelessness services, we talk a lot about resource allocation, conditional among the group of people who apply for housing, essentially. And one thing that's been really revelatory from this work is learning about how much work there is to do just to get people into the pipeline. And if we can kind of expand the sphere to have a more kind of like end-to-end or even more end-to-end kind of understanding, that would be really valuable. So we're really trying to expand the scope of consideration. So that's the setup and related work. Any questions? That was a long. Okay, Let's go ahead and talk about more specifically what is specifically new to our paper in terms of the optimal annotation probabilities and what they value. So we're starting off with this estimator. And essentially what we want to do is find the annotation probabilities, minimize the asymptotic variance subject to the sampling budget. So the asymptotic variance is going to be the kind of like limiting bound on the noise in our estimation. It depends on certain quantities about our problem, like how rarely treatment is assigned, as well as the outcome conditional variance, sigma squared for each treatment value. And the outcome conditional variance sigma squared of x is just about, how hard is it to predict the outcomes from the covariates that you have. And importantly, in this asymptotic variance, the probability of appearing data, the probability of annotating data points also appears. That is what we control, so we're going to optimize over it. And it also interacts with the kind of treatment rarity and the outcome conditional variance. So what we want to do is solve this optimization problem. Once we solve that optimization problem, to give a sense of what is the actual thing we're going to do with it, we're going to do like a batch adaptive allocation, which is to say that in the first stage, we're going to have like a pilot stage where we randomly assign some proportion of the budget to the data. That's because we need to learn the outcome model and the propensity score. So we'll randomly sample, get some pilot estimates of the outcome model and propensity score. And we'll use those pilot estimates to estimate the optimal data annotation probabilities. And in the last stage, we will randomly sample so that our final data sets looks as though the data points were sampled according to these optimal probabilities. So in terms of related work, in terms of this method, the ideas build a lot on adaptive treatment allocation. We're actually building on a quite kind of like early paper in this line of work. There's very close connection to bandits and sample red. You can call this like pure exploration and so on. But the thing is that just that in this data annotation setting, a lot of these more complicated or finer notions like in-sample regrets are less kind of appealing. And also doing this in batch is a lot easier for human annotators because they take different amounts of time to complete. So you don't want to kind of like wait for one annotation to come in before continuing your allocation. So I'll just say it's a very rich kind of like parallel technical literature about bandits and so on. In some senses, we're working with a very simple notion here, but I would argue that it's actually enough for the task of data annotation. So that's what like the shape of the algorithm looks like, or what we want to do eventually looks like. I'll talk about some of our results. So first of all, we can solve for these annotation probabilities. We can solve for what they look like in closed form, and their form is fairly intuitive. The optimal sampling probabilities are proportional to like a kind of like mean average deviation, so the square root of the conditional variance divided by the propensity score. And this looks kind of natural because if outcomes are really hard to predict, that makes your variance much larger. And you definitely want to make sure that you kind of like cover that with ground truth. If the propensity score is very small, if the propensity score is very small, it was very rare to observe this treatment. It's going to contribute a lot to your estimator. And therefore, you also want to make sure that you cover that with ground truth. So the optimal sampling probabilities take this form. It's very interpretable and intuitive. So even if you don't want to kind of like run like a full-blown optimization kind of thing, you can just calculate this ratio and sort your data points by it and do something based on these kind of like very natural or intuitive principles. So that's the form of these optimal annotation probabilities. They have a nice natural intuition. There are some other kind of like causal specific insights that we can gain from the form of these optimal propensity scores. So we can kind of go ahead and plug back in these optimal probabilities into the estimator. And the biggest thing to observe from that is that in doing so, these optimal annotation probabilities are essentially trying to kill the propensity score. So what that means is that the optimal causal estimator that you can achieve is independent of the propensity score. It just depends on the underlying unpredictability of outcomes. And this has some implications for what kind of causal estimators that you should run on the final data set. So there's a different class of causal estimators that don't try to kind of estimate all of these pieces separately, like the propensity score, and then plug them into this division. You can imagine that when you're trying to estimate propensities, which could be very small, when you put them in the denominator, your estimator might blow up. So this often happens in practice. When we look at experiments about adaptive treatment allocation, this also happens a lot in their papers, and they start to introduce some kind of like mixing or smoothing. We suggest that actually you should try to use different kinds of causal estimators that estimate this inverse function directly. So what they do is they do some kind of like clever tricks to try to estimate this function in one shot, essentially, without first estimating this thing and then dividing by it. I won't go into details about like how that happens, but if you look up like balancing weights or Reese representer, a lot of people work on these kinds of problems. So what is the takeaway? If you're doing all this work to try to figure out the optimal annotation probabilities, essentially they're trying to kill the propensity score. And so you should use methods for causal estimation that don't try to estimate the propensity score itself. This is also true of non-causal estimation papers as well, like PPI and so on and so forth, that depend on this kind of like adaptive treatment allocation. Other kinds of insights that we can get, we can study like when is this actually helpful? When is this better than just doing random sampling and applying the same estimator? You can always do that, just do random sampling. And again, we can study this kind of like relative efficiency question. And really, it's if your budgets are smaller, our approach is more helpful. Or if your propensities are more imbalanced, if you're more sensitive to rare treatments, then specifically targeting the ground truth for the rare treatments is also gets you more improvements. So just to conclude, we think it's nice that when you study this in closed form, you can get some insights about optimal data annotation that are hopefully useful, even if you don't do like end-to-end adaptive allocation. So where's causally best to sample? As you imagine, depends on some of the quirks of the causal estimator, where outcomes are harder to predict, and where treatment is really rarely observed. The best case outcome for this kind of optimal causal inference approach is actually to try to like kill the propensity, kill the causal hardness of the problem, and just be like normal mean estimation. And so this changes the estimators that we recommend to a strong emphasis on balancing weights rather than plug-in estimators. And this is particularly helpful under small budgets or under treatment imbalance. So those are some of the insights from the closed form probabilities. How do we achieve those optimal probabilities? It's with this two-stage kind of adaptive procedure. So we have a first pilot stage where we estimate these propensities and outcome model and conditional variance. You still need to estimate them to figure out what are the closed form probabilities. But what we do is we recommend that you use balancing estimates on the kind of final data set. So you use those pilot estimates to sample a data set of ground truth, and you combine it all in the final analysis. We show our main result is that you can study this kind of adaptive procedure, and at least asymptotically, you'll still get valid statistical inference that achieves this optimal asymptotic variance. What does this kind of like statistical result buy you? Again, this a little ground truth and the capacity to do this adaptive annotation can get you statistically valid and better inference. So this will be asymptotically normal at the optimal variance, kind of like asymptotically as these estimates converge and so on. So I want to show you some results to talk about, how much do these improvements look like? What can they actually get you in practice? So I'll start with some simulated and semi-simulated data, just because we actually have the ground truth outcomes. And so we know what the kind of like true average treatment effect should be. So these plots show what is the mean squared error of our estimator. On the x-axis over here, as we're going from left to right, we're increasing our budget from 10% to 60% of the data set. The simulated data is over here, and we have 3 different estimators. So the main baseline we're comparing to is random sampling with the same kind of estimator. That's in blue, this dashed line. In orange, like orange-red, is our adaptive allocation version. If we plug in like the doubly robust estimator, so if we kind of like plug in the inverse propensity score and the pi function directly. And in dashed green is our adaptive allocation. We're running like a balancing estimator on the full data set. So this kind of like shift that I recommended to use balancing estimators that estimate the inverse function in one shot. The main takeaway is that you can achieve improvements in estimation quite quickly with adaptive allocation. This beats random sampling, especially at smaller fractions of the data set. So you can achieve at the smallest budgets, like a 70 to 90% reduction in mean squared error. If we want to translate that to like a kind of budget saved metric, if we think about how much data budget you need to achieve the same kind of like log width of your confidence intervals, or the same width of the confidence intervals, you can save 10 to 45% of your data annotation budget to achieve the same kind of precision or same kind of confidence interval width. And so, for example, I'll talk about this later, but yeah, so that's if a budget saving method kind of makes that more salient. So this method can be quite helpful, especially at lower budgets, which kind of lines up with what we said before and what you might imagine from the intuition. So next, I'll talk about a kind of application to the breaking ground data, or this case note data. Now with this case note data, we're actually still working on annotating even our kind of like smaller active client cohort. So what we're going to do is we're going to start off with a methodological illustration where we're going to think about our outcome as our highest placement. I also said that this outreach is a very kind of like longitudinal thing. So we're also going to simplify matters for the causal inference by thinking about this as a static intervention, by kind of collapsing time buckets. So we're going to think about treatment as the number of times that you receive outreach in the first 6 months. So we're going to pull a cohort, like a 2-year cohort of clients from the entire data sets. And this 2-year cohort means that everyone will be kind of like aligned in that they were seen like relatively often throughout the whole cohort. So we're going to kind of like restrict our sample in order to try to aim for internal validity, because there's obviously a lot of fundamental like measurement issues that are very also highly correlated with outcomes. So we're going to try to we're going to kind of restrict the cohort and look internally for internal validity. The X covariates we're going to look at, we can consider 2 variations. It could be either like tabular data, which is kind of like not as rich. We might augment this with Casenotes. So we're going to think about what is the effect of more or less outreach in the first 6 months over this 2-year period on an outcome, which is essentially going to be like an index variable of the highest housing placement that is received over that next 1.5-year period. So housing placements, there's a couple different kind of categories. So we're going to kind of arbitrarily assign them numbers on a scale of like 0, 1 for kind of like transitional, housing, 2 for temporary, and 3 for permanent supportive. The kind of like numbering of this is a little arbitrary, but the idea that these get more stable as the numbers get higher is there. And the estimate, and we're going to also kind of discretize outreach into different intensities. So we're going to look at quantiles of how much outreach that people receive. And we're going to kind of look at incremental effects of more or less outreach between bin 2 and bin 3. So bin 2 is kind of between like 5 and 50 contacts in 6 months. Bin 3 is between like 50 or 100 contacts in 6 months. So there's a lot of kind of like collapsing being done here, but that's how we will kind of put this into a static causal inference problem. So what we find here is that ultimately housing placements are quite noisy. So our confidence intervals still kind of include 0, but we still find a similar story in terms of how optimal data annotation with a small budget can help you recover the precision of much larger budgets with random sampling. So we find that you can greatly reduce the mean squared error. We also, but ultimately this is limited by the ultimate kind of like variability of the outcome. So our kind of future and ongoing work includes kind of taking a more kind of like fully dynamic approach to the problem, so not collapsing everything in time so much. But at least this is a proof of concept that for this housing placement outcome, you can achieve a lot of these same benefits in terms of precision under a very small budget, like 10 to 20%. And the idea is that this kind of budget saves lets you actually really like open this data set for analysis because it's much less resource intensive to kind of ask these questions rigorously, basically. So this is more of a proof of concept from, because we're using housing placement as an outcome. But we are still able to find the same message. You can really improve the mean squared error under a really small budget, like 20% or 30%. Okay, one thing I'll mention is how do we incorporate LLMs into this? So we can think about different kind of like augmentations of our original prediction problem. And here are the like variants of the outcome modeling that I was kind of discussing. So the first thing that we could do is start with the tabular data. It's quite coarse. It's mostly discrete data about like what kind of programs this client is in, what kind of demographics they have, how long have they been with working ground, as well as like different kind of keywords. So ultimately, this tabular data is pretty coarse. We can try different levels of like augmentation of this data. So we can add pre-treatment case notes. We do this by kind of making a summary of these pre-treatment case notes. And when we're augmenting this prediction with text, what we're doing is then kind of really just serialized tabular prediction, which is to say we kind of read the data out loud, append the summary, and then add the LLM, ask the LLM, like, what is your prediction given this information? So very like zero shot can be improved. We also work on like fine-tuning. Fine-tuning helps these models as well. So this is a very basic way of doing things. And then we also combine the LLM prediction or the serialized LLM prediction and with a final kind of ensembled machine learning prediction that includes both this like tabular only prediction and the serialized LLM prediction. And so why at the end do we do this ensembling? Other papers kind of like in this LLM assisted inference line of work also this kind of ensembling, and it's really because our method ultimately is sensitive to like the error patterns of the predictor. So serialized LLM prediction has like a much more unknown kind of like error pattern structure. It's much harder to learn. Versus black box machine learning classification, you have a lot more control over kind of like how smooth that error structure is, that error pattern is. And we do find that although these kind of augmentations improve predictive power, the amount of improvement that you get in terms of the optimal data annotation is a bit attenuated by the fact that their errors become harder to predict. So it is true that they have better predictive power for just the outcomes independent of anything else. But for the optimal data annotation, what matters is how easy are their outcomes to predict as well. So that's a kind of walkthrough of the project so far. This is kind of like the part 0 where we figure out how do you even kind of like ask causal questions with these kinds of qualitatively coded outcomes. There's a lot of ongoing work, ongoing and future work that we're excited about. We want to go back to this classification schema and extract these kinds of crucial outputs and relate them to nonprofit outcomes. So kind of going back to like coding, like how far are they in progressing towards completing a housing application and so on, and investigating what is the relationship between like completing a housing application, starting a housing application, these intermediate milestones, and the down the line housing placements. We're recruiting MSW data annotators for sessions, which is really exciting for kind of like data annotation sessions. We're also working on a kind of like fully dynamic analysis of the relationship between outreach and outcomes. And we're also exploring with the nonprofits, like maybe more practical or day-to-day practical uses of LLMs, for example, summaries of case notes. What should they look like? How do we improve them? So on and so forth. So I'll wrap up there. The main message that I want to give from the talk is a little bit of ground truth can go a long way to really unpacking these really rich data sets that can help us get a sense of some of the really rich stuff that happens in a lot of these kinds of situations close to AI and society. So we worked today on kind of like the part 0 of this, like how do we figure out where to optimally annotate data, specifically for causal inference. So another big takeaway is like what you're trying to use the annotations for will also affect what is the best way to do the data annotation. Yeah, that's the main message. A little ground truth will go a really long way for unpacking this value. So I'll wrap up there. I'm happy to take any questions.
Any questions from the audience? We're close to the 5 p.m. mark, but we can probably take 1 or 2 questions. If you have any.
I have a quick question. So hopefully kind of a simple question, but I was curious, like you have a large client population and like a huge data set of your case notes, and then you run this analysis, get your estimations. Now, 3 months from now, you have even more case notes, but it's the same population. Can you use like the outcome of the last time you ran this analysis, or do you have to kind of start it blind as if like you had it run a previous prediction?
Yeah, that's a good question. I think you can use the existing analysis as a starting point, and you can think about like which extra people should I annotate. Does that make sense? Yeah.
I guess relatedly, how frequently or when do we know we should be updating like the gold standard ground truth data? Like what are is there any signals that inform, oh, this is maybe a time point, or maybe if certain things happen, then we should be considering updating our ground truth and especially with the annotation part.
Yeah, that's a really good question, especially because you could do this not in just like one batch, but like many batches or like really live or like continually. There's some work in kind of like performance monitoring of like ML models in general, where you can kind of like adaptively track an outcome and see how how when it starts to drift, like then you might like do some kind of like retraining. I would have to think it's not immediately clear like what metrics you would track for this kind of situation. Because the problem with causal inference is you never get an observation of ground truth as your, so it's a little bit different than with like mean estimation. So you can track performance metrics for like the outcome models, for example, but you never really get a signal for what is a true causal effect that you can track the delta to. So I think that's one wrinkle for the causal setting. Yeah.
Last call for questions.
I have a question. And I don't know how much you can answer this. This might be a question more for like the boarding team or the social work team, but like to what extent, so you're having MSW students as the human annotators, which is good. I'm just curious if there's any involvement of people with lived experience, I'm thinking on the very early side of this project, like to inform actually what kinds of ground truth data to be collecting that they know is related to specific housing outcomes. Like if there's any involvement of those types of stakeholders in this process and the plan of the process, whether it's through the annotation, through initial kind of feedback about what different kinds of data maybe should caseworkers be collecting in the first place. That reflects their lived experience with the housing pipeline. Also, like, are people with lived experience involved at all in verifying kind of results of these models or their plans to?
Yeah, that's a great question. Unfortunately not, but we would love to think about how to do that and where especially to do that. I will say that even this what ended up being in the classification schema ended up being very instrumental and kind of disconnected from experience, as it were, or lived experience. And I think another challenge that is in tension with that is a lot of the case notes themselves. The case notes are pretty short, and so they also don't necessarily capture things that might be particularly relevant. And so then it becomes kind of like a larger question of like, well, we can try to do better labeling of this from the case notes, but that kind of thing also probably doesn't appear in the case notes as it is.
Yeah, and that's kind of
So
what
I think
is that there might be different types of data that need to be collected. Because I'm just thinking about my experience. My partner does a lot of professional work and also just personal civic life work in homelessness outreach here in Los Angeles. And it's like this housing pipeline, as you capture it, is not linear. Like there's a lot of relapsing back, and a lot of that has to do with like things that probably are not captured in CaseNet, like things that are very much about that person, what's going on with them, something happened, and they fell 2 steps back in that process. And so it complicates your job. Like it's super, super challenging, but you see that a lot, and I don't know how to think about that from like a data curation perspective.
But I think it's very relevant. I think I should also say we tried to explore other schema, maybe can we measure rapport or something like that. And very quickly we realized that is not something that is in the case. So,
All right, let's give Angela another round of applause.